This is your part 2 video for 8.2 areas in the plane. And in part 1, we looked at integrating with respect to x, where we were looking at our left and our right bounds as far as we were going from what x value to what x value. But there are many cases where it's easier to integrate with respect to y rather than with respect to x. These are some visuals of where it might be easier to have your function in terms of y or in terms of x. Most of these are not going to be functions because they do, if you would do the vertical line test, they would not pass that, they would fail that. But with these cases, instead of looking at your curve as top minus bottom, with these ones, you're looking at right minus left. And for your bounds, you're going from bottom to top instead of left to right. So these are just some different visuals. You can see with the red one, we have C and D as our bounds where we're bound in between. For the green one in the middle, C is given to us, and then D is where the curves intersect. And then the blue one over here, C and D are both intersections of those curves. So again, just some representations of where it might be useful to integrate with respect to y rather than x. So we're going to go back and revisit that example 4, and I'm going to write those equations up here so that you guys have them. I'm not going to redraw the picture, but you can look back at the notes or at the PDF for that. So my two curves that I had were y equals x minus 2 and y equals the square root of x. Now, if you're integrating with respect to, actually, I might redraw the picture because I think it would be good to have that visual there. If you're integrating with respect to y instead of respect to x, you need to have x equals equations instead of y equals equations. So this top equation, instead of y equals x minus 2, that's going to be x equals y plus 2. The bottom one then, instead of y equals the square root of x, that's going to be x equals y squared. However, that's only for the y's that are greater than 0, because again, I couldn't put, I can't get back a negative y value from the previous one, so you do need to keep in mind those original bounds. So here's what my curves look like. So I had this, and then I had this one coming up at 2, and crossing the line at 4. So I had this. So this is the area that we are looking to find. Well, you almost want to tilt your head sideways on this because you want to know which curve is always on the right and which curve is always on the left. Well, the red curve, which was the linear function, this one is always going to be on the right, and then the blue curve there, the parabola or the square root, this one is always going to be on the left. So it's right minus left instead of top minus bottom. So whenever I set up and do my integration, it's going to be y plus 2 minus y squared, and then of course this is going to be a dy instead of a dx because I'm integrating with respect to y. Now for bounds, you want to look at where your lower bound is and where your top bound is. Well, the lowest that we go here is 0. The highest that we go, this point, which I know doesn't quite line up there, that y value is 2. So instead of integrating from 0 to 2 and then 2 to 4, I'm going to be integrating the y's from 0 to 2. This is going to be a whole lot easier to integrate than what we had to deal with in the last question. Because in example 4, remember we had to integrate the square root of x, and we ended up with 2/3 x to the 3/2 power. And that can just be ridiculously messy. Whereas this one, whenever I integrate this, I'm going to get 1/2 y squared plus 2y minus 1/3 y cubed. That's what I'm integrating from 0 to 2. Plus, whenever I plug the 0 into this, all of those terms are going to turn into 0. So there's not even going to be as much algebra to do. So I have 1/2 times 2 squared plus 2 times 2 minus 1/3 times 2 to the third. So that's plugging in the 2. When I plug in 0, I'm just going to get 0. 0 squared is 0, 2 times 0 is 0, 0 cubed is 0, so I'm just going to be getting 0 there. So if we go through, 2 squared is 4, half of that is 2, 2 times 2 is 4, 2 cubed is 8 times negative 1/3, so minus 8/3, and then when you do the algebra and simplify that, you end up with 10/3, which was exactly the same answer that we got in example 4. It's just that the math was a whole lot easier. So this is a case where integrating with respect to y is much, much easier than going with the integrating with respect to x. Now for example 6, it says find the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. We are going to use our graphing calculator to integrate this, but the first thing I want to do is decide, do we want to use integrating with respect to x or with respect to y? Well, if I integrate with respect to y, I would have to solve the first equation for x. So x would be equal to y to the 1/3 power. That's not really that difficult. I don't have to put a plus or minus. But the second equation is already x equals. If I were to integrate that one with respect to x and have to get the y by itself, I would have to add the 2 and then take the square root. I would have a plus and a minus with that. So we would actually have to set up 2 different integrals. So this one, the y integration, is going to be easier. The y integration is going to be much easier. You can use the x integration to get a visual of what you have here, but the integrating with respect to y is definitely going to be the easier way. So this is going to be x equals y to the 1/3 power. I am going to set this up. I'm going to have to use the calculator to figure out where the intersections are and which one is on top, which one is on bottom. So I do want to think about this. This is just for the graphing calculator. Y squared is equal to x plus 2. Y is equal to plus or minus the square root of x plus 2. So let's go back to y equals, and I want to look at this. So we have our 2 equations are x to the third, and then we have, I can't do plus or minus all in one, so I have to do the square root of x plus 2, and then I have to do negative the square root of x plus 2. And then I can look at the graph of that and see what I'm going to be dealing with. So there's the first one. There's the second one. And there's the third one. So remember, the red and the black actually are going to represent the same curve when it's x equals y to the 1/3 power. But the blue curve, that is the original, the blue curve is the one. The red and the black do represent the same thing, but those are the x equals y squared minus 2 equations. So it looks like the blue curve is always going to be on the right, and the red and black curves, those are always going to be on the left. So whenever I set up what I'm doing, so the blue curve is the y to the 1/3 power, and then the other curve is the y squared minus 2. And again, that's dy. Now I have to figure out my intersections. So this is bottom to top. Remember, I am looking at the y coordinates here, so I want to know my intersection down here. That's going to be between the blue and the black. Notice that it jumped to the red. So those ones are going to intersect at -1. So -1 is going to be my bottom bound. My top bound then, I need to get up here. You do want to make sure you have the correct curve. So the blue curve is good. And then the red curve is where it intersects on the top. And this one is going to be decimal, 1.2148623. So 1.2, I'm sorry, I used the wrong value there. I even said, and this is, again, one of the things that will keep you up about that. I'm not looking at the x value, I'm going to be looking at the y value for this. So I'm not using the 1.2148623, I'm using the y value, the 1.793, and so on. Now with the first one, it didn't matter because the x and the y were the same. It was -1, -1, so I don't actually have to go back and fix that one. So I have 1.793003715. Sorry if I was confusing about that. Again, it's really easy to get confused because you're so used to looking at the x values. But if you're integrating with respect to y, then you need the y values. This is not something we can do by hand easily because of that top bound. So I am going to go back to my calculator and use that to find my value. So I'm going to do math 9. -1 is on the bottom. 1.793003715. And then I have to type in my equation. So that's going to be, I am actually going to type in x instead of y here, but because I use y as all my reference, it's going to be the same. So y to the 1/3 power, even though it says an x, minus the quantity of y squared minus 2. I'm going to close that and then come out of there and do an x. And really it doesn't matter what variable you use as long as whatever variable you use in the equation matches the variable of integration. So we're doing some thinking there. The problem is a little more complex, so it might take a little bit longer to come up with a solution. But there we have it. 4.215 would be your solution. And that's units squared. So 4.215 units squared. Again, rounding to 3 decimal places on the AP exam, that's something you might have to get into the habit of. I did keep more decimal points with my intersection coordinate because I wanted to make sure that that was accurate, and then I'm just going to round my answer at the end. Okay, so this is the last one. Example 7. Find the area of the region. In example 4, notice we're going back and revisiting that same example by subtracting the area of the triangular region from the area under the square root curve. So we're going to go ahead and draw these again. Here's my 2 and my 4. 1, 2. This is going to be coming up like that. I am going to stop it at 4 because I know that's where my curve is going to stop. And then I have this region. So there's what I'm finding. So if I'm finding this region, I can actually find the entire area under the curve because this is using the geometry there. So if I look at the integral from 0 to 4 of the square root of x I can actually, because basically, if it weren't for that triangle, that green section would extend to the rest of the area underneath the curve for the square root of x. So I can subtract out that triangular region, and it would give me the same answer as what we had going through and separating under integrals. Now this isn't always going to work this way. This one works out nicely because I do have a triangle, and I can easily find the area of that. It's 1/2 base times height. So I'm basically going to find the area under the curve of the square root, and I'm going to subtract 2 from it. So this is 2/3 x to the 3/2 power, evaluated from 0 to 4, and then I'm going to subtract 2. So this is 2/3 4 to the 3/2 power, again minus 0, because when you plug in 0, you're going to get 0, minus 2. 4 to the 3/2 power, we can take the square root of 4, and that's going to be 2. Then to the 3rd power is going to be 8. So 2/3 of 8, and then subtract 2 from that. Surprise, surprise, you still get the 10/3 like you got before. And I think this one was even easier than integrating with respect to y. We didn't have to write nearly as much because I was able to use geometry and just subtract out that triangular region from the curve. So we had 3 different ways to look at the same type of question. All 3 are correct. Some just involve a little bit more work. This section is pretty important. I've seen this come up very, very frequently in free response questions. Sometimes it'll come up in a multiple choice question, but really free response is most likely where you're going to see this. So this is something that you do want to focus on. Please go back through, rewatch this video, rewatch the part 1 video. There are other videos that are going to be linked online for you to get some extra assistance if you're still not understanding this. And reach out to me if you have any questions.